Good evening. I am Mamta Kumari from Agriculture and Soils Department, and today's lecture is on remote sensing and GIS applications in crop inventory and cropping system analysis. So earlier also, crop inventory has been done as the part of land cover mapping, but remote sensing and GIS application has shown its tremendous potential for these kind of studies. Because I think all of us already know after so many lectures, because remote sensing has potential for accelerated survey, it can have the synaptic view over the area. Apart from that, it can collect the information in various spectral regions, which varies from visible to microwave regions, so that it makes the data collection possible in monsoon season also in the fully cloud cover area. Then apart from that, we can discriminate various crops growing in the area simultaneously using the multi-temporal data. So because of repetitive coverage, we can collect the data, we can differentiate various crop types as well as different crop growth stages. So why crop inventory and cropping system analysis is important? Major areas of application in crop inventory using RS and GIS are crop acreage estimation, crop yield prediction and modeling or estimation, agricultural drought assessment or crop growth stress monitoring, and cropping pattern or system analysis. Getting the knowledge about crop acreage or crop yield estimate is important for the export-import price negotiation, for agricultural planning, for price regulations, etc. Apart from that, it can be used to know the cropping pattern or crop distribution in the study area. Along with this, it can see the changes in the crop rotation or cropping pattern. So that's why crop acreage estimation and crop inventory, cropping system analysis, etc. are important. We can see how much area has been converted from crop to any other land use land cover type, or how much area has been brought under agriculture from shifting agriculture into the permanent agriculture. So that's what the importance of crop inventory analysis. In India, it is very difficult to use remote sensing techniques for crop inventory assessment because of so many reasons. In India, farmers have very small holdings. So because of very small field sizes, it is very difficult to discriminate all those crop types growing in those fields using the coarse resolution satellite data. So to resolve that issue, one must use high resolution satellite data like LIS4, Cartosat LIS4 merged product, or Iconos or QuickBird. So these two LIS4 or LIS4 Cartosat merged product is Indian product, available at low prices. Then large diversity of crops grown in an area. This is because every farmers have their different requirement, and as there is large diversity of crops, there will be spectral mixing if we are using limited number of spectral bands. So to resolve this issue, we must use as many as possible as many spectral bands like visible, near infrared, sphere, then mid infrared, microwave, etc. Apart from that, high radiometric resolution data also used, because if radiometric resolution is high, anybody can discriminate or can differentiate the amount of reflectance or emittance coming from the smaller amount of reflectance or emittance coming from the two different areas. Then there is large field-to-field variability in sowing and harvesting dates. There is difference in the management practices as well as cultural practices. So to resolve this, multi-temporal satellite data should be used. For example, there are so many areas in which wheat and mustard grows simultaneously. Because these two crops grown simultaneously both are giving similar kind of spectral signature if we are using single satellite data. But both are different as per the crop duration. Mustard and wheat both are sown in the month of November, but mustard is harvested much earlier to that of wheat. So if we are able to collect the data of March, then we can discriminate mustard and wheat as per their crop growth profile or NDVI profile. Then large area under rainfed agriculture, which results into the very poor crop canopy. Then in this, we should use some soil adjusted vegetation index like SAVI, which removes the effect of or minimizes the effect of soil background reflectance. Then there is practice of mixed and intercropping kind of thing. For this, to resolve this, we must use high spatial resolution satellite data like LIS4 or Cartoset product, merged product, which I have already mentioned. Then there is always extensive cloud cover or fog or haze condition in various parts of this various seasons. Like in monsoon season, it is always overcast by the cloud. In Rabi season, there is problem of haze. So to resolve this issue, we must use SAR data. SAR data has capability to penetrate the cloud. So nowadays, reset one data is there, which can be used resolve this issue. Remote sensing data in crop inventory has been started by CAPE. CAPE is Crop Acreage and Production Estimation. This is a joint program by the Ministry of Agriculture as well as ISRO. So under this, two objectives were there. First is to get the state level average. First, to develop a methodology to get the state level acreage and production estimation. Some important crops, and second is to transfer this technology to state level agencies for operational application. So under this, for crop acreage estimation, two approaches were used. First is small area crop inventory or complete enumeration approach. Under this technology, actually this type of methodology is used for smaller area or district level, taluka level area. So in a satellite image, whatever pixel is coming under district, that area is subtracted, and whatever pixel is coming under that district boundary is analyzed for crop acreage estimation. But for large area, like for state level or group of districts, sample segment approach is used. In sample segment approach, there are various steps. First, there is sampling plan preparation. In this sampling plan preparation, first stratification is used. Under this stratification, first and foremost, different strata. Strata is nothing group of homogeneous population. These are formed based on either agroclimate or agrophysical basis, or by crop vigor basis, or by crop density basis. So first, stratification or different strata are formed on the basis of these criteria or characteristics. After that, under these strata, again over these strata, square grids are overlaid. These square grids are nothing, just the sample segments. So after overlaying these grids, one must select these grids. So what should be the size of grids? It varies. It varies as per the requirement. If area is homogeneous, then bigger sample segment is also sufficient, like 10 km by 10 km sample segment size. If area is heterogeneous, this means many crops are growing in that area, or there is large heterogeneity because of sowing and harvesting rate, then one must go for the small sample segment size, like 5 km by 5 km. So all those sample segments are overlaid over the strata, and on the basis of random point table, Some of the sample segments are selected. Then how these sample segments are selected? These are also dependent on crop characteristics. What are the collateral data available in that area? Collateral data means what is topographical map, thematic map. Thematic means existing land use, land cover map, then soil map, climatic data, everything. So on the basis of that, on the basis of all the collateral data as well as crop characteristics, these sample segments are selected. Then apart from that, previous year remote sensing apps products are also used to mark these sample segments over the satellite data so that ground data can be collected. Generally, ground data are collected in 3 phases: pre-field, in-season, as well as post-field survey. Pre-field are collected to know the sowing date, what is the sowing date, what kind of crop calendar is here, and other ancillary information, or land use, what would be the land use, land cover type in that area. Then in-season field should be collected. It should be near synchronous to the satellite pass, or real-time synchronous to the satellite pass. In this, what is the crop vigor, crop density, crop type, probable harvesting date in the future, all these kind of data are collected. Then in a post-field survey, this survey is done for the accuracy assessment. So in this particularly post-field survey, from the accuracy assessment point of view, all these data are collected, like harvesting date and what kind of crop cover is there, it is confirmed. Then after this, one more thing is there, how much area it should cover, how much sample segment we should cover. So whatever number of sample segments are there in these strata, at least we should go for 10% of sample segment. However, it is okay for the state level of acreage estimation, but it has not given the uniform kind of result in the district level of crop acreage estimation. So in this we can see various training sites are selected. So after sample segment, sample plan preparation, we do classification of remote sensing data or digital analysis of remote sensing data. So there are 2 types of digital analysis or visual interpretation. Earlier visual interpretation was also done, but visual interpretation, there are so many demerits. First, it is suitable for small area. Second, it varies from interpreter to interpreter. And third, it can't utilize all the spectral information. Like in list 3, 4 bands are there, but in visual interpretation, we can use only 3 bands information as FCC, as for visual interpretation. And in this, basically, tone, texture, all the visual interpretation tools are used, and interpretation legends are found. So, sorry, excuse me. In CAPE, as the digital analysis, maximum likelihood classifier algorithms has been used. In this, whatever pixels, this algorithm basically groups all the pixel corresponding to the or closer to the training site pixel. Other classification techniques are also available, like neural network, then object-oriented classification, but all those classification techniques are under development and are not being used operationally. Like for high resolution data, there is variability in a single crop also. Like for a single crop, pixels varies, pixel reflectance varies. So instead of bringing that pixel into single class, we get the several kind of classes. So for that, object-oriented classification is used, which considers the field size as well as pixel information also. So homogeneous segments are formed on the basis of some thresholds, user-defined thresholds. And after forming those segments, those are compared with the, excuse me, those segments are compared with the training size. After that, Gaussian or maximum likelihood classifier are used. So that kind of classification is good for high resolution satellite data, where variability is more within a single crop also. Then to differentiate different types of crops growing simultaneously in an area, decision rule-based classification is being used. In this, first, as this is multi-temporal data, so volume of data is large. So first thing is co-registration. Satellite data must be co-registered with the other satellite data. Then second, radiometric normalization. As all the data are collected during different dates of the season, so there will be difference in the atmospheric condition. So all these data must be corrected with as per the atmospheric hindrance. Then, as volume of data is more, and in all the satellite data, different spectral bands are there. So instead of using whole satellite data, some data reduction techniques are used by either by PCA or by some indices calculation, vegetation indices calculation like NDVI. And growth profile of all those vegetation indices are compared, discriminate one crop from another crop. So this is digital analysis of the satellite data in all those sample segments. So all those sample segments are classified using remote sensing data. After that, there is aggregation of crop acreage. How to aggregate? First, we calculate the histogram in the sample segment, which tells us about the crop proportion in the sample segment. Crop proportion means what is the crop area, crop proportion in percentage in that sample segment. So if we know the crop proportion of sample segment, then one sample segment, then simultaneously we calculate the crop proportion in all the segments, sample segments in the strata. After that, we take the mean of crop proportion in the strata. So that is the mean value of the crop proportion. After that, we multiply this with the individual sample segment area. We have mean of crop proportion of each each segment. What varies? There is variability in the crop area in each stratum. Once we multiply, we get the crop acreage in that stratum. After adding all these, we get the crop acreage in stratum, and after that, simultaneously, after overlaying the district boundary or taluka boundary or state boundary, we get the crop acreage for particular district or particular state. After that, accuracy assessment is done. In accuracy assessment, this is nothing, this is the matching or what is the accuracy of classified satellite data or acreage estimated, acreage estimated by the satellite data, and what the ground truth collected in the field. So we match this using the confusion matrix, and we see what is the accuracy in terms of overall accuracy or omission error or commission error. Then we do the statistical analysis with respect to some reference. Two terms are used. One is precision, another one is bias. Precision is tells us about the reliability of the crop acreage, whatever estimates we have produced. Reliability in terms of repeatability. So how many times we have got the similar kind of result using the same procedure. So that is the precision. And bias tells us about the how much our estimated value is closer to the true value. So for good estimate, one must have the good precision or high precision and low bias. So high precision and low bias tells about the good estimate of crop acreage. Precision is measured by the coefficient of variation, while bias is measured by the relative deviation. Relative deviation with respect to some standard. In that, basically Directorate of Economics and Statistics values are used. So suppose we have crop yield after crop acreage, after putting the yield values, estimating the yield values, we have yield estimated by the satellite data, and if we subtract the Directorate of Economics and GIS data, yield data, and divide it by the again remote sensing data, then we can get the deviation from the standard value. If that deviation is less than 10%, then it is acceptable. So we need 90 by 90 accuracy for the crop acreage estimation. Fasal is the advancement or advanced stage of the CAPE. After the successful result from the CAPE, Fasal has been started. Fasal is nothing but forecasting agricultural output using space, agrometeorology and land observation. So here we are using the conventional approach by the econometry as well as agrometeorological information. Agrometeorological means weather data, climatic data. Then along with the field observation, we are using the high resolution as well as moderate resolution satellite data for various outputs like what is the crop area, what is the crop condition, acreage or yield. And this has been started to give the multiple in-season forecast. So we can see here that pre-season, early season, mid-season, pre-harvest as well as state level as well as district level harvests are given by the Fasal concept. This is developed by the ISRO, and in year 2012 Fasal concept has been transferred to Ministry of Agriculture. So Ministry of Agriculture, one new center has been started, MNCFC, Mahalanobis National Crop Forecast Center in New Delhi. Now they are using Fasal for the crop yield estimation or crop acreage estimation for operational basis. This is showing the accuracy evaluation of national wheat production forecast using remote sensing. Here we can see that the forecasted wheat yield as per the acreage performance as well as production, that is yield per total yield, are compared with the Directorate of Economics and Statistics as per the graph, and these are the closeness as per the relative deviation. Relative deviation I have already spoken. It is the difference between remote sensing estimated value and Department of DES estimated value, and it is per unit remote sensing estimated value. Again, I was not clear. Again, I will say RD is equal to RS value minus DS value divided by RS. That RS means remotely sensed values. In Fasal, use of microwave data was also started. So that thing was very much different. Along with the in-season forecast, use of microwave data was also added for the Kharif season or monsoon season crop assessment, crop yield assessment and acreage assessment. So here this is the plot showing the backscatter sigma naught variation in different dates, and this green graph is the rice plot. Here we can see this actually. Now I will discuss the principle behind the discrimination of rice with respect to other crops. This is the pre-transplantation where yes, crop, there is no crop, but only exposed crop, soil is there. And this is the transplantation phase. backscatter value is very low in the water ponding condition because it gives the specular reflectance. Specular reflectance goes away from the sensor, SAR sensor. So it gives the very dark appearance or very low sigma naught value. That's why in the crop growth profile, uh, during the transplanting phase, we get the sudden reduction in the sigma naught value. And this particular feature discriminates it from the other crop. You can see here there is no reduction in the sigma naught as compared to the rice crop. And as there is increase in the crop growth, sigma naught increase. So it is little different from the NDVI profile, where in NDVI profile we start with the lower values and then we get some peak and then we get again after harvesting we get the lower value. In using microwave data, first there is a high value due to transplanting condition, water ponding condition, we have low, and then it increases with respect to crop growth stages. So this microwave or SAR data is being used for rice assessment as well as jute assessment in the India. For other Rabi season crop, optical data are being used. So this is an inventory map using the, I'll show you this some images from different sensors. This is LIS3, FCC. This is the crop inventory map of LIS3 data. Actually, this is of area Bhopal. Bhopal is in the major crop is pulse. So from yellow color we can see the different pulses areas. So this is for different area using LIS3 only. LIS3 has a spatial resolution of 23.5 meter. This is of LIS2 and again FCC crop inventory map using the LIS1. LIS1 is of 72 meter spatial resolution. So here I wanted to show you the relative deviations of the crop acreage. As we are using coarse resolution satellite data, our accuracy or relative deviation is increasing with respect to some standard or DES values. Like for wheat, for pulse, here we can see in all cases we have got the higher relative RD value in percentage if we are going or moving towards the coarse spatial resolution data. One more thing, if we have the confusion in the same kind of crop at different places, then instead of taking one signature for a particular crop, we must take a different kind of signature to take the high vigor, moderate vigor or low vigor into account. So it is always better to categorize in this manner so that we can get the better result. This is a similar kind of result, but here instead of single data, merged product are used with PAN. PAN is 5 meter resolution data. So here we taken the advantage of high spatial resolution and spectral bands information from the LIS3 data. So it has been used for the village crop inventory map. This is Iconos data. Here we can see different kind of individual features also we can see. Similarly for quick bird data also, here we can discriminate the similar kind of canopy growing in the area just by the some object oriented classification. This is showing the WIPS data. WIPS data of 188 meter. Again FCC and crop inventory map. WIPS data, whenever we are using WIPS data or AWIPS data, nowadays we are using AWIPS data of 56 meter spatial resolution. We use multi-temporal data and we use this for the state level and again India basis. Then second was the yield estimation or modeling. Different type of crop yield models are available, but whenever we want to use for the operational basis, we must select something which is simple to use, not very complex, and it can be applied for whole state or whole India basis. So time to time different models are developed, like empirical model, semi-empirical model, or physical process based model. So generally for operational basis, empirical models are used. Those empirical models are developed for particular area, and it is specific for particular area. We can't apply one model developed for one area to the other area. Like various types of models are spectral yield models, agromet spectral yield models, integrated yield models, or some model which is linked with the CGMS, that is crop growth sim model, with the GIS. So spectral yield model, we are considering the vegetation indices. So we are developing the model or equation between the satellite derived vegetation index and yield of that area. Yield we are getting from the crop cutting experiment, or historical yields also, along with the historical remote sensing satellite data. Then in agromet spectral yield model, along with the vegetation index, we are considering the meteorological indices as well. Like we are taking the temperature data, temperature difference of in terms of degree days, that is average T average minus T base at different growth stages, that is flowering or reproductive stage. So one thing I have forgotten to tell you, that in a spectral yield model, if we are using the single date data, we must take the peak crop growth stage data. Peak crop growth stage means heading or flowering stage data. So that is one thing. Second thing, if we are after developing the model in the current season, if we are not able to get the peak crop growth season data, then we must do the time correction. This means from the historical developed model, we using the crop growth profile, we have to adjust the current season spectral index or a spectral vegetation index. Integrated yield model. In integrated yield model, along with the spectral vegetation index and climatic data, we are utilizing the soil as well as management data also into the account. So using the soil data, using the climate data, we are developing some agroclimate index, and then along with this agroclimatic index as well as spectral vegetation index, we are as per the integration, we are relating this with the yield, and we are developing the integrated yield model. Then in crop growth simulation model, actually this one is the physical process based model. It is complex. Here we are intended to estimate the crop growth variables as well as crop yield. Along with that, we are trying to see the how it is varying, how our soil, plant, water or nutrient balances are varying as per the environmental conditions as well as crop management practices. So environmental condition means we are considering the solar radiation, we are considering the temperature of that area, air temperature of that area, everything, weather parameter, climatic parameter. We are saving soil layer, we are saving crop management practices layer, we are saving the boundary, etc., everything related with the crop into the GIS, and we are linking that GIS data with the crop growth simulation model to estimate the crop yield. So these kind of indices are used. Basically these are mostly used, like ratio vegetation index, NDVI, then transformed vegetation index, perpendicular vegetation index, atmospherically resistance vegetation index. So these are the index basically used. Sometimes instead of directly using the vegetation index, some crop growth variable are estimated, like leaf area index. Leaf area index is an important parameter which considers the exchange of energy as well as mass along as per the environment. Like by this we can estimate the evapotranspiration, we can see the photosynthesis activity. So leaf area index, if we are able to see, we can relate this with the crop yield in better way. So first, relate between LAI and index is developed, and using that LAI crop yield is estimated. So these are the two maps showing the LAI map as well as yield map. These are various agromet spectral yield model. Here we can see like in this vegetation index is used, in this trend is used in this meteorological information like T2, TD3, etc. is used. What is the whatever full form is there, it is given below here. Our integrated yield model, as we have already discussed, agroclimatic yield index is developed using soil map, then air temperature, that is weather data, meteorological data, and irrigation potential map. After that, agroclimatic yield index is developed, and then after taking the satellite data also into the account, after developing yield model, yield prediction is done. So this is equation which we can see here. We have taken the spectral vegetation index as well as agroclimatic yield index also into the account. This is an example of process linking the process-based model, crop growth simulation model with the GIS. So different inputs are taken, stored into the GIS, and then different RDBMS are formed, and this gives the continuous result at some certain fixed interval, time interval, 1 day, if we have daily weather data. Apart from that, under the crop inventory, drought monitoring or vegetation condition, crop condition are also being assessed. So for drought monitoring, NADAMs are being implemented on operational basis by MNCFC only. So they are taking various indices like NDVI, say, and then various precipitation data from grain gauge as well as TRMM satellite, and then they are using soil balanced energy model also to consider the soil profile moisture movement. So on all these parameters, they are assessing the drought. So drought, actually it has already been covered in different lectures, so I'll not go in that. Then cropping system. So first, what is cropping system? Actually, I think it is the yearly sequence, and most importantly, spatial arranged crops or crop and fallow in the given area. So what kind of cropping pattern is there? It is totally dependent on in that area how many crops we have taken in the season, how many we have taken in an year, and what is the spatial distribution of that crop in an area. So once you have crop inventory map or land use map, agricultural land use map from two different seasons, you can integrate these two maps to produce the cropping pattern map. The crop rotation is the repetitive cultivation of an ordered succession of crops or crop or fallow on the same land. So once you have cropping pattern, you have crop rotation, you can analyze, and if you have ancillary information like management practices, then we can analyze the cropping system. So cropping system is the cropping pattern and their management to derive maximum benefits from a given resource base. Using the remote sensing data, we can derive cropping pattern, we can derive crop rotation, we can derive crop calendar, and various remote sensing derived indices. Cropping pattern and crop rotation are derived using different season land use, land cover, or crop inventory map. Crop calendar is derived by using the NDVI growth profile curve. Here we get the sowing time, sowing date, harvesting date, and the total duration. So if we have the crop growth profile crop calendar as per the pixel basis, we can analyze the cropping system in that area. Now let us see some remotely sensed derived cropping pattern indices or cropping system indices. So mostly three indices are used. One is multiple cropping index or multiple cropping intensity MCI, and another one is cultivated land utilization index CLUI, and the third one is area diversity index. MCI is mostly used in for the to analyze the cropping system. This is ratio of total area cropped in an year to the total land area available. So here in formula we can see whatever area is coming for a particular crop. For example, we have rice, we are growing rice in wheat in another season, some area in, and we consider fallow also. So out of 100 we are utilizing 60 in the season for rice growth, for growing rice. We are utilizing again 60 to grow the wheat crop in the rabi season. So as per this formula, 60 plus 60 divided by 100 into 100. Your MCI multiple cropping index will be 120. So this MCI tells you about the vertical intensity, vertical profile of crops grown in a year. MCI, if it is 100%, this means this is basically we are growing single crop. So it is not like that, because sometimes some crop area are fallow and some area are cropped, and it varies from season to season. As per the whatever crops we are growing, 100 means basically we are taking single growing single crops in single season, and 200 at least we are taking two crops in a year, whatever area available. Then second is CLUI. CLUI, it is the product of land area planted to each crop multiplied by the actual duration of that crop, and it is divided by the total land area available into the number of days in year 365. So I'll just give an example here. Like rice is 150 days crop. You are utilizing 60 hectare area for rice. So we will multiply 60 with 150 again, plus 60 hectare for wheat multiplied with the 120 days for the crop growth, because generally 4 months are used for the wheat crop growth. So if we divide it by 100 into 365, whatever value we will get, that is CLUI. It tells that in an year when and where land has been not utilized. Then third index is area diversity index. Actually it tells us about the diversity of crops grown in an area. Here AI is again area under each crop, and N is the total number of crops grown in a year. So more number of crops, more diversity of the crops in that area. I'll give one example that in what condition it would be seen. Suppose we are taking rice in one season and again rice in another season. So this is a monocrop kind of. However, we are taking two crops in a year, multiple cropping intensity will be high, but your area diversity index would be low, because we have not diversified. Then one example is like cotton wheat system there. Cotton and wheat system is a long duration cropping pattern. As compared to this, we have a potato gram cropping system or gram potato, whatever, some short duration. So multiple cropping index as well as area diversity index would be high because we are taking two crops in a year and we are taking two types of crops in a year. But cultivated land utilization index CLUI would be higher for the first condition, that is for long duration crop. Why? Because in a year, most of the time crops were present on the land. So that's what crop cultivated land utilization index tells, that when and where land has been left unutilized. If we are taking long duration of crops or more number of crops, this means our land is busy throughout the year, CLUI would be higher. This value will be higher. So in every case, this value might differ. So multiple cropping index tells us about that which kind of crops we should take. Area diversity, how many types of crops we should take, what would be the ideal condition. And CLUI generally used for the fine tuning of the cropping pattern. So there are requirements of the change in the cropping system in different conditions. Sometimes we are not growing sufficient area, we are not utilizing sufficient area available for agriculture because of poor resource availability. Sometimes we are taking similar kind of crops year by year because of more market demand, but we are deteriorating the soil. Sometimes we are taking cereal after cereal like rice wheat cropping system, which is harmful because we must consider some pulses in between to restore the nutrient of the soil or potential of the soil. So in that condition, we must go change in the cropping system. So this is the thing, like tillage requirement. One example is there. Rice wheat cropping system is there. In rice, we are growing crop in the puddled condition. So in puddled condition, we are destroying the soil structure and we are blocking the pore spaces. So what happens? A hard pan is formed in the subsurface. To grow the crop, we have to dry the area land. Then we must break the hard pan which is being formed by the during the rice crop growth puddling. So if that is formed in the subsoil, then what will happen? That there will be poor root growth. There will be hindrance in the root growth for the wheat. So year by year, if we are taking these kind of crops which are taking two contrast physical environment, then we are destroying our soil. So this is the motive behind studying the cropping pattern analysis and to recommend any kind of change. So this is a flow chart showing how we can utilize the remote sensing data as well as GIS data to prepare the cropping pattern map as well as how it can be utilized and what kind of data are required. I have already told, like in Kharif season, in monsoon season, there is requirement of SAR data. In Rabi season, optical data is also sufficient, and one third season is like Zaid season or summer season. If we have all these maps, we can logically integrate that into the GIS, and then we can prepare the crop rotation map. If we are using the more than 1 year satellite data, we can have crop remotely sensed derived the indices, cropping pattern indices. In GIS, we can store the weather data, we can store the boundary, district boundary, then we can analyze all these data after overlaying over the cropping system map, cropping pattern map. And after analyzing the long-term data, we can suggest some alternate step also as per the expert knowledge. So this is just one graph. This is a crop inventory map for the Kharif season, monsoon season. This is for Rabi season, and this is cropping pattern map, which is produced by integrating these two crop inventory map. This is just showing the spectral profile crop calendar in the study area to analyze how many crops are growing and what is its temporal distribution. So this was done in the West Bengal, and here all these indexes are given. I have not discussed the range of index value, which I will show in the coming slide. So here one thing is low value means poor performance. So wherever multiple cropping index is low, this means there is a requirement of bringing most of the land into the cropped area. So this means we are utilizing very less agricultural area. And area diversity index, if it is low, this means we are basically taking similar kind of crops in the area. And cumulative land utilization index means most of the part of the year was fallow. So this is the range of different indices. MCI value, if it is less than 130, then it is low value, and if it is low value, there is need of or requirement of intensification. Then ADI value less than 2 is less, CLUI value less than 0.5 is less. So whatever has been done, this as per this study, some recommendations are given as per the result for different districts in the West Bengal. Like if MCI is high, ADI is high, this is very ideal condition, you have to maintain this thing. But if MCI is low, ADI is low, everything is low, this means we must go for intensification, we must go for diversification also. We must include some pulses which can improve the soil health. So this is one case study for the Punjab state, and in this state, first agroclimatic map, agroecological zones were produced using the soil map, using the climatic data. Actually, this is the reason behind this. We all know that in Punjab, there is water depth has been increased, which is leading to salinity and water logging in the area. And to remove this, and apart from that, we are taking the similar kind of crops year by year. We are not changing our cropping pattern. So to remove this problem, to tackle this problem, these three major steps are there. First, divide the state into different ecological zones. Then, what is the present status of cropping system by generating the crop inventory map and logically integrating into the GIS. Another method is that if we have whole year NDVI data, then just by layer stacking those NDVI profile at once, we can generate the crop pattern map. We need not to generate two crop inventory and logical integration. We need not to go for that. Then third is by the expert knowledge on the basis of existing soil condition, on the basis of existing agroecological zones, some alternate crop diversification plan for the entire state has to be proposed. So this is the agroecological zone delineation on the basis of climatic data, temperature data, length of growing period, which is totally based on rainfall data as well as potential evapotranspiration data, then soil data as well as biomass, soil data by NBSS LUP, biomass data by satellite data, NDVI derived biomass. So various scenes have been taken, coarse resolution spot data at 1 kilometer by 1 kilometer data are considered, and crop rotation map was generated. We can see here most of the area is coming under rice wheat crop system, another is cotton wheat. Both are very intensive nutrient demanding kind of crops, and we can observe there is no inclusion of pulses or even agroforestry. So on the basis of existing agroclimatic zones, these are agroclimatic zones, biomass on the basis of existing biomass, soil type, existing cropping pattern, or cropping patterns were suggested for different crop growth season for Kharif and Rabi and summer. So most of the portion we can see that agroforestry or sugarcane kind of things are bajra, coarse cereals, etc. are suggested to break the nutrient demand as well as water demand. Rice is basically high water demanding crop. Okay, thank you.